So I'm doing this for a number of facts now on the subject of climate and energy, is to explain just why you should not believe what you're told when experts tell you it. And this is a major, major one that goes completely unchallenged by anybody, as far as I'm aware. I know one or two people who are aware of the problem, but it's not in any way publicly debated. So here we go. It's about the pH of the oceans and the fact and fiction of what you're told. And the question really is 0.1 pH less alkalinity really 30% more acidity? Because that is what you are told it is by NASA, NOAA, and anybody who's repeating what they're told. If you have questions about this, I have an email there. I put my Twitter account on as a free bit of promotion for Brian, and I really would like to thank Tom for this opportunity. Now, this is not really for me to talk to, it's for you to keep as points or just keep it on your screen, take a shot of it. These are all the points that I will be making. NASA and UNESCO et al., you can go and look this up anywhere on the web, will tell you that the oceans have become more acidic by 30% because of a change in pH from 8.2 to 8.1. I would suggest that this is wholly false and a misrepresentation of the scale and the value it contains, the tiny URL in the first bullet. I want to be clear about what people are being told. And in this case, children are being told by NASA. And if you go there, you will find, just to make my point, an initial point that I then attack, is that children are being told that the oceans are acidifying rapidly due to human activity, which is damaging life and etc., threatening ocean life, and that increase is 30% increase in acidity. NASA says that, and it's telling children that. And this is just terribly wrong, because it's not true. pH is a scale presented by a gentleman called Søren Sørensen at the Carlsberg labs in Denmark, the brewery maker. And what he wanted to do was to describe a scale, or to produce a scale, which described how the chemical action of an aqueous solution, i.e. one made of water, with water as its base, how that would change in acidity and alkalinity. And he did this by by using the number of ions that are of hydrogen for the acidic part of the scale, and the number of hydroxyl ions, which are OH and are negatively charged, to do the alkaline part of the scale. There we go. This is the ionic basis of the pH scale. Okay. And if you look at the scale, you'll see that the range from 0 to 14 pH, this is the ionic basis of pH. And what it explains is crucial to what is being done to misrepresent the scale. You'll see there that the range goes from highly acidic at 0 to neutral at 7 pH, and then from neutral 7 pH to 14 on an alkaline scale. Now, if you look to the left of that, you'll see what that is actually derived from. Those numbers are the indices, and this is where you need a bit of mathematics, are the indexes to the base 10 of the actual number of ions. So if you look at, for instance, black coffee, you have a pH of 5, which is 100 times the neutral. If you go to 1, it's 1,000,000 times, etc., etc. So the ionic scale here, this is the important part. The ionic scale is from 10 million in one direction to 10 million in the other direction, or 20 million. In fact, that's 10 times 10. That's 100 trillion, the range that you're talking about, or 10 to the 14 if you're really mathematical. So the ionic range is 100 trillion from 0 pH to 14 pH. And the little pretty pictures at the side show you where we are with seawater. Sorry, I'm looking at my graph. You can see seawater has got a lot of OH ions in it, and say black coffee has a lot of red hydrogen ions. Note that seawater is always alkaline. It's always dominated by OH ions, hydroxyl ions. So it's never acidic. And to say that it becomes more acidic when it's becoming less alkaline is an obvious deceit. That's my first simple point. Now let's go to how much less alkaline it is for the 0.1 pH. Looking again at the graph, the 0.1 pH between 8 and 9 there. It's between, what is it, borax and seawater. It's a load of borax. And now I've gone back to, because this is basically a numeric point, I've gone back to what is being done to create this 30% or 25%, whatever it is they say, difference in acidity, which isn't, it's a reduction in alkalinity, that using this ionic scale creates, or what they use this ionic scale to create, to deliver. First of all, the actual change in the pH scale, which is what defines the alkalinity and acidity of a solution, is 1.2%. Okay, and that is the real point. It's 1.2% pH. It's not 25%. So what is done here is the experts say, oh, really, you've got to look at the ionic concentration. And what they do is they take 10 to the power 8.1 and 10 to the power 8.2, and they subtract one, they compare one to the other, and that gives them a ratio of 25% change. But that's meaningless, because these two numbers, which are 126 million and 158 million, exist within a whole range now of 10 to the 14, which is 200 trillion, did I say earlier? A lot. So what, in 100 trillion, 100 times 10 to the 12, 100 million ions. Now, if you do that comparison and you take the difference between 126 million and 158 million, which are the antilogs of the two pHs, you get 0.00032% of the full scale range. That's how significant this change really is on the ionic scale. Ratioing the two pHs antilogged is a completely misleading idea. And it's nothing to do with the pH scale, of course. So these claims are both deceitful and numerically 1,000,000 times wrong. And I hope I made that clear. These claims are deceitful because they're manipulating the numbers to make 1.2% pH look like 25% acidity change. And they are saying that this is making an alkaline solution more acidic. No, it isn't. It's making it less alkaline. And in fact, of course, the changes are almost immaterial in the ocean. And they talk about, oh, the Great Barrier Reef must be protected from this, etc. There's nothing wrong with the Great Barrier Reef. It's fine. And you can, then there are lots of people producing models to show that this and that might be happening to the shells of crustaceans, but they're models, they're not real. It's not based on observation. It's all prediction using a model, which should be familiar to you in the predictions of massive climate change that actually have never happened. Just a little 1.5 degrees since 1850. So that's all I wanted to say. The other thing about the ocean is, if you do get interested in this, do please go and check. Just look up the pH scale on Wikipedia and read how it was created and how the science works. And also you'll find that the ocean is a highly buffered solution. Now, here we have our 8.2 pH seawater, or now it's 8.1 pH. And because it's highly buffered, if we squirt a little bit of a polluting substance into it, this carbon dioxide loaded water, like that, it will resist any change. Okay, it does not like being changed. It has a chemistry which resists a change in pH by any polluting substance that's added to it. Cheers. So that's my demo. There is nothing about the use of this, the science of pH, that is respected by the people who are making these claims. Okay. And I would be happy to debate that with anybody who cares to come up with an alternative position.
Do you even believe that the pH of the oceans has changed by 0.1? Do we know what it is to that level of detail? Do we know that?
My answer to this question is the same as my answer to is CO2 causing climate change? The answer is yes, it is. But how much? Can we really measure that? I think in the case of CO2 we can, but that's a whole other talk. Mm-hmm. Yes, it may have changed a bit, but do we know if that change is natural or caused by a tiny bit of CO2? No, because just to mention, just to try and answer your point another way, 98% of all the CO2 on the planet is in the oceans, on the surface of the planet. Not quite sure what's down in the magma. 98% of it is in the oceans, and it varies slightly according to how hot or cold the planet is. So let's see now, if under Henry's law, if the planet gets warmer, we'd have more CO2 in the atmosphere, which is less CO2 in the oceans. So I think it's easy to, I think they probably made a lot of measurements, and yes, I reasonably convinced, although it's a very small change, that it's probably got a bit less alkaline. But is that due to a natural or a human cause? Impossible to know.
Okay. And out there in the real ocean, though, there must be a mixture of pHs, right? It's not a consistent 8.1 everywhere in the whole ocean.
Yes. Is the short answer. There is a volume of work on that I have not read. What I've done here is address the actual physical science of the chemical scale, which I can do very well because I'm a physicist, not a chemist. I've read a few papers, as you may have gathered from some of the things I said earlier, about how it's affecting life within the oceans and how these shells might grow a bit and those might not. But it's all models and it's all based on prediction, and we know that the Great Barrier Reef, which is one of their favourites because nobody goes there to look at it much, is fine. If you go and go and talk to the people who work on the Great Barrier Reef, apparently they don't know what the problem is, and it has record coral cover pretty much. And every time there's a big storm, it gets damaged and it grows back again. If it gets a bit warmer, the coral expels the current. There's a name for the things that live in the coral that make it live and colourful. It expels those and gets some new ones that work better at a different temperature. That's how the coral sea works. So all of these things are quite natural. And there's certainly no evidence that coral cover has been severely changed in any way on the Great Barrier Reef by the weather. There is by climate. Sorry, there is by climate. There is by the weather, because they have these big storms that whack it one.
We're being sold this whole idea that there are creatures in the ocean that if the pH changes by 0.1, they're going to die and go extinct. But I would say as a layman that they would have gone extinct long ago if that was enough to kill them off. They have to be resilient, and they must be making this up.
You'd be right. And of course, the point is that corals have been on Earth for millions of years through much warmer periods when there was no ice on the planet, before the ice ages. So, and if there are all sorts of different corals as well. There's not just the corals that are the coral sea corals, if you like, the classic corals of the Great Barrier Reef. There are deep water corals off England, cold water. There are corals that live at depth and also much colder temperatures. So the corals are amazingly prolific things. They're continually emitting whatever it is, the seedy things to propagate. They're continually propagating, and they get into the ocean currents. And guess what? Wherever the conditions are right, they propagate. And if the conditions change in one, become better somewhere else, that's where you'll find more of them.
So I'm looking at a headline here. I've seen it a lot over the years. Why ocean acidification is the, quote, evil twin of climate change.
Yeah. Well, it is it? Why would they need to say that it's more acidic when it's not? And that it's a 25% change. Most of the people who write these articles believe this tosh. That it's 25% more acidic. And it's just a manufactured number, which is of no meaning. The only thing that has meaning is the actual pH scale, the indices value of the index value of the pH scale. That's why the pH scale was created by Sorensen and is accepted and used globally, because it describes quite well how things work.
All right. Thank you very much, Brian Catt. We will talk to you next time. Goodbye.
Pleasure.